Quickhull is an algorithm used to compute the convex hull of a set of points. The convex hull is the smallest polygonal shape which surrounds a set of points. This means that for every pair set of points C and D, a line can be drawn between these points, and that line lies within the convex hull. So why are convex hulls important? So convex hulls are widely used in sports analysis for both analysing football playing styles and basketball defensive formations. Generally in football, when a team has a larger convex hull, it shows that they are attacking, whereas when a team has a smaller convex hull, it shows that they are trying to defend. It's also useful in data science, where it is used for onion peeling to calculate the convex layers of a dataset. Using convex layers can find the outliers in a dataset by removing the outermost convex layer and also identifying the centre of a dataset by identifying the innermost convex layer. Similar to Quicksort, Quickhull is a divide and conquer algorithm in which the aim is to recursively partition the dataset to identify convex hull points in different areas of the dataset, disregarding points which cannot possibly be in the convex hull. So how does the Quickhull algorithm actually work? So the first step is to find the minimum x and maximum x points in the set of points. The second step is to form a line between the 2 points, creating 2 sets of points, one above the line and one below. This line acts as the partition line. Step 3, so for each partition set, you need to find the maximum distance point from the partition line. This is then added to the convex hull and is used to form a triangle between the maximum distance points and the 2 points in the previous partition line. All points in the triangle are disregarded from the convex hull search, as they cannot possibly be in the convex hull. In step 4, 2 sets of points are formed by the 2 triangular lines. If there are points which exist outside the triangle, these are recursively processed using step 3, in which the maximum distance point in each partition is found. So as you can see by the screen, the red lines are now the lines which are being used for partitioning, and the maximum distance points are being found in each partition and then added to the convex hull. Since there are no more points outside of the triangles, the convex hull is formed and the recursion stops. So this is my implementation of Quickhull. So in lines 11 and 12, I find the minimum x point and the maximum x point. And then in 20 and 21, I form these into 2 sets, ones that lie above the directed line and ones that lie below the directed line. So the points to the right function simply just finds the points which lie to the right of a directed line. So S1 in this case would be points below the line and S2 would be points above the line. In lines 24 and 25, I use the find hull function to find the convex hull surrounding each of these partitions. And then in 31, I add the 2 hulls together to get my convex hull. So find hull is the function which does most of the work. Find hull is a recursive function, so it has a base case where the length of points is 0. And when that happens, then the first point in the partition line is just returned to be placed inside the convex hull. When the length of points is 0, this means that there are no points outside of the triangle to be processed to try and find the points in the convex hull. So lines 45 to 53 just find the point which is most distant from the partition line. Then lines 55 to 57 split the data into 2 subsections, ignoring points which fall within the triangle formed. And this does it by finding points to the right of the directed line formed between both the start point to the furthest point and the furthest point to the end point. This creates 2 partitions. So lines 61 to 62 recursively calculates the convex hull of these 2 partitions, and then line 63 returns the sum of the 2 convex hulls.